This video is all about how to make choices when you're making a complex molecule, such as this one on the screen now. This is an intermediate in the synthesis of the Aplyronines by the Paterson Group. I'll put some links in the description below. This is part of a much bigger molecule that was the target of a total synthesis, but it highlights options that you might take based on different types of selectivity and easiness of the reaction to perform in a lab, particularly on large scales, which are required in early stages of big total syntheses. To start with, I'll sketch out the retrosynthesis to highlight some key issues. Just having a scan over the molecule to see what we're dealing with. On the left-hand side, we've got an alkyl iodide. This is arguably the most reactive part of this molecule. It's in there ready to do a nucleophilic substitution reaction in the future. In the middle, we've got an acetal, but actually that's been used strategically as a protecting group for a 1,3-diol here. It's just a convenient way of doing it. This type of protecting group is usually abbreviated as PMP. That's paramethoxyphenol. It's one of many things we could pick there, but it turns out that one's helpful for determining stereochemistry for us, and there's no particular reason not to use it. And it's quite useful later on in the total synthesis. Now, that protecting group is spanning these 4 stereocenters, sometimes referred to as a stereotetrad. These things are quite common in polyketide natural products. This is a polypropionate type one. That means alternating oxygen and methyl-bearing stereocenters. But fundamentally, the oxygens are related in a 1,3 fashion, so the type of disconnection we should be looking for is going to use enolates or aldol type chemistry. Next up, we've got a diene. Now, there are lots of ways of making CC double bonds, but I think in this total synthesis, there was a particularly cool way of doing this, which we'll uncover later in this video, so keep watching if you want to find out more. At the far end of the molecule, we've just got another protecting group. That's just a silyl ether. This one is sometimes abbreviated to TBDMS. That's tert-butyl dimethyl silyl, but that itself is often abbreviated further, just as TBS for short. One quick note is that these protecting groups are orthogonal. This means that there are conditions that allow us to take one of them off at a time, which is quite an important control element in a synthesis. So I'm just going to skip a few steps in the retrosynthesis to highlight the key issues. The key disconnection is to find somewhere in the middle of the molecule, and we're going to exploit aldol chemistry, as we noted before. This will split the molecule nicely into 2 bits, and what we need is something like this. We need an ethyl ketone that looks like this. What we have here is another protecting group. This is called a PMB group. That's paramethoxybenzyl. This is protecting a hydroxyl group, so good disconnections for making alkyl halides in general is to come from an alcohol on the same carbon. We can note that this molecule only has 1 stereocenter now, so this one is absolutely key. We're going to use this one to set all of the other ones in our synthesis. So the plan in the synthesis would be to enolize here on the ethyl ketone. That should be easy enough. That's the less hindered side. And then we'll react it with an aldehyde. So perhaps something sensible will be like this one here. Now, we've actually exposed a control problem here in that in doing an aldol type reaction, we're going to need to expose this aldehyde to acid or base, or Lewis acid or Lewis base. And it's pretty risky to do so with this one because of these alpha protons next to the aldehyde. For example, if this gets a sniff of a Lewis acid, the proton in purple becomes much more acidic, and we risk tautomerization to an enol type form. That's just La for Lewis acid as an example. But we can see in doing so, we've now made an extended conjugated system, which won't necessarily isomerize back to the one we started with, particularly when there's an option to pick up a proton in that distal position, like with these green arrows. There's a very strong probability that we'll just isomerize the double bonds into conjugation. This will be thermodynamically more favorable, but in our case, not what we want. So we're going to have to think quite carefully about this diene. In fact, it's going to have to be masked or protected in an aldol reaction, most likely. We'll come back to the Paterson strategy for this, as it influences heavily what our starting material will be. Just a final note in the retrosynthesis, this ethyl ketone is quite easy to get hold of. It's a few steps away from this chiral pool intermediate. This is known as Roche ester. That's the company Roche. This is available in the chiral pool as both enantiomers, so it can be quite useful in synthesis as a source of optically pure stereocenter, and has been used commonly over the last few decades for this type of work. And now we can have a look at the full forward synthesis and have a think about why certain reactions were chosen over other possibilities. But if you're enjoying the video so far, if you could give the video a like and consider subscribing to my channel, it's really helpful feedback for me that I'm making videos that people enjoy. Now, first we can look at how they make the aldehyde. We need to find some way of masking the diene at this point so that it doesn't get messed around with in an aldol reaction. The starting material they went for is this one, 5-hexyne-1-ol, which is commercially available. Might not be massively obvious where we're going with this at the moment, but do bear with it. We've got functional groups at both ends of that molecule. So the first step will be to protect one end so that we can react at the other. So what we're going to go for is temporarily protect the hydroxyl group. Now, there are loads of options for us there, but this is really early in a big multi-step synthesis. We need to be able to do this easily at large scale and ideally as cheaply as possible. So although in normal circumstances, this wouldn't be my favorite protecting group choice, it works out particularly well here to protect as a THP acetal. This stands for tetrahydropyran. And the way that this works is that we use this reagent that has an enol ether present. This is dihydropyran, or DHP. If we treat that with catalytic acid, we make this oxycarbenium ion, which can then be attacked directly by our alcohol. And this acetal is reasonably stable, so useful as a protecting group, provided you don't treat the molecule with too much acid until you want to take it off again. The reason why this one isn't my favorite protecting group is that it brings a whole load of mess to particularly the proton NMR spectrum, which really isn't ideal. Just having a look at that structure in 3D, all of these hydrogens are in different environments, and so have their own little multiplet in the NMR spectrum. I can just get in the way because they'll be all over the 1 to 5 ppm range. But with this protecting group on a relatively simple starting material, it's not too much hassle as long as we don't keep it around for too long, which is the plan in this synthesis. So having temporarily protected using the THP acetal, the next step in the synthesis is to remove the acidic proton that's on the alkyne. That has a pKa of about 25, so it's reasonably easy to take. A clean way of doing this would be to use butyl lithium. That will give us a nucleophile that looks a bit like this, with that negative charge housed in an sp hybrid orbital. That explains why the pKa was so low. This conjugate base has a negative charge in an orbital that has 50% s character, so is a lot lower in energy than we might have expected for a negative charge on a carbon. So we need to find an electrophile for it now, and here we use methyl chloroformate. The chloride is by far the better leaving group on that carbonyl species. So here we're adding one extra carbon to our chain length and also an ester functional group. And the reason why we're doing this is that this inoate ester is going to hide the diene functional group for us. As we can see, the diene itself is an isomer of the alkyne, just with the hydrogens on those 4 atoms positioned differently. Later, after the key aldol disconnection, we can do an isomerization to reveal the functional group that we actually want. Right then, so next in our synthesis, the job of the THP acetal is done, so we can take it off. This is done using PPTS methanol. This is just a mild acid source and a nucleophile. It stands for pyridinium paratosal sulfonate, which is much easier understood as a structure. So that's just a tosylate anion and a pyridinium cation. This is a very mild and easy to use crystalline solid in the lab. So all you need there is a catalytic amount of it, and the reverse of the acetal formation that's over on the left-hand side of this page will occur to give us back the free alcohol. And then we're almost there for our key aldehyde. Now, there are, of course, loads of reactions that we can use to do this sort of thing. Very common options might involve a Swern or a Des-Martin oxidation, or using PCC or PDC, essentially some sort of chromate source. But in this synthesis, we should still bear in mind the practicalities of doing this reaction, because we could well be wanting to do this on a 50 or 100 gram scale. We want to make sure it's operationally easy. And for example, some disadvantages of the Swern oxidation involve it has to be held at minus 78 degrees for a bit, which is pretty tricky on large scale. Des-Martin, you've got a very chunky reagent, as in it's got a high molecular weight. So we're going to need access to a very large mass of reagent. We'll also generate a very large mass of byproduct. So there are complications involved there. Any of the chromate sources, again, get a bit hairy on a large scale. The chromate reagent itself is pretty toxic. It's a potent carcinogen, and handling it on scale isn't something I'd want to do particularly. So the Paterson Group went for a different type of oxidation, using a sulfur trioxide pyridine complex in DMSO with triethylamine. This is possibly a less well-known oxidation. This is the Parik-During oxidation. It's related to the Swern oxidation, which involves activating the DMSO. DMSO is just dimethyl sulfoxide, and in doing so, we can make an activated sulfur intermediate, which can oxidize our substrate. The mechanism looks something like this, just for a generic alcohol. It's quite common with curly arrows to represent a sulfoxide as this charge-separated resonance structure. That reflects that the pi bonding between sulfur and oxygen isn't as strong as it often is, because there's a big size difference between sulfur and oxygen. Firstly, the sulfur trioxide will be attacked by the oxygen on the DMSO to generate an intermediate like this. That's probably reversible. Here we've generated the potential for a sulfate leaving group, and so our alcohol can now come in and displace it. We'll lose a proton at this point because there's loads of amines floating around, either the pyridine or the triethylamine, and we'll be left with the same intermediate we would get in a Swern oxidation, for example. This has a reasonably acidic proton on one of the methyl groups, which can be taken by the triethylamine base, and the sulfene type intermediate that we get in the middle here can collapse to give us the aldehyde that we want, and dimethyl sulfide, which is reasonably easy to remove as a byproduct, even if it is a bit stinky. Okay, and that completes the aldehyde synthesis. So moving forwards, here's our other starting material, the Roche ester from the chiral pool, which is enantiomerically pure. First thing we're going to do is protect the alcohol with a PMB group. Because this alcohol is particularly susceptible to E1CB type eliminations, and the molecule itself susceptible to retro-aldol fragmentations, we can't easily use basic conditions here. So we're going to use PMB TCA, that's the trichloroacetamidate. I've discussed these reagents in some other videos of mine recently, so do check them out. The mechanism is in the one linked in the description below. If I use this reagent, which is essentially the paramethoxybenzyl group with a fancy leaving group on it, I can get the reaction to occur just using a mild acid. In fact, you can use the PPTS acid that we used before, and this is just a very mild way of protecting to give this PMB ether. Next step, I need to play around with the ester. In fact, I need to turn the ester into an ethyl ketone. Now, I can't just use ethyl magnesium bromide, like a Grignard reagent here, for example, because otherwise I'll get double addition. Although we'll form an ethyl ketone intermediate, it'll be formed in the presence of ethyl magnesium bromide itself and will react to give the tertiary alcohol. So we need to find a way of stopping it halfway. And a classic way of doing this is to use the Weinreb amide. To do that, we use this methylated hydroxylamine in the presence of isopropyl magnesium chloride, which is just commercially available. To form this product, which is a type of Weinreb amide, these can be useful for stopping reactions so-called halfway to get us the product that we want. Just to be clear on the mechanism here, at low temperature, the isopropyl magnesium chloride is only a strong base. It's too hindered as a nucleophile in lots of organic chemistry. So what we're doing is deprotonating the amine. It's going to have a pK of around 35. So we need quite a strong base to do that, to generate this nitrogen nucleophile, which can just do a substitution for the ester. The amide bond in the product is less reactive than the ester in the starting material, so we get good control in this reaction. Next step, we get the Weinreb amide and react it with ethyl magnesium bromide. Again, that's commercially available, or you can make it yourself, I guess, if you wanted to. And that will take us to the ethyl ketone that we wanted to. Now, the reason why these conditions work is that we're actually doing this at low temperature and then using an acid workup. The reason why this works and prevents double addition is that this intermediate is stable at low temperature, and that's because the magnesium is getting involved. Something along the lines of this as a chelated up structure. This is stable at low temperature, so we don't isolate this. We wait for it to form, and then we quench the reaction with acid, which will collapse the hemiaminal. That's the oxygen and the nitrogen on the same atom, to spit out the hydroxylamine byproduct and leave us with the ethyl ketone that we wanted. Okay, and now we're ready for an aldol reaction. The way that this is done is to first form the enolate, and we're going to use soft enolization conditions here using cyclohexyl boron chloride and triethylamine, because these are standard conditions for forming E-enolate equivalents. I've gone into the details of these in other videos. I'll link them in the description below if you want to check them out. So we don't isolate this intermediate. All we have to do with it is cool it down to minus 78 degrees. This will maximize kinetic control, and then react it with the aldehydes that we made earlier. Now, this is quite a complex transformation to explain, but it'd be extremely highly diastereoselective for this diastereomer of product. What's happened in this reaction is essentially the stereocenter in the starting material in the enolate, which I'm just highlighting with a red star, is doing a lot of the work. If we have a look at the enolate, the E geometry of the enolate is also helping. Via a Zinnemann-Traxler six-membered ring transition state, that will translate over into this anti-relationship in the product across the newly formed carbon-carbon bond. But we have to put a bit more work in to work out why we get that specific anti-relationship, as in the up then down, going left to right, rather than the down then up. I'm intending to make a really big video on aldol reactions at some point, but just for now I can highlight the key control elements, the first of which comes from the enolate itself. it actually has a single preferred conformation due to restricted rotation about this bond. Now, the restricted rotation can be explained by the Hauck model, because there's a situation here where we need to minimize 1,3 allylic strain, as well as minimizing some 1,2 strain. Just down in the bottom right-hand corner, the preferred conformation will have the hydrogen on the stereocenter eclipsing with the methyl group on the enolate. And that means we have the methyl group, or the methylene O, P, and B group, on either side of that molecule. This will have a consequence in the aldol reaction, as in the transition state, it's more favorable for the aldehyde to react on the top face as drawn with the OPMB group, as opposed to the opposite face with the methyl group. Now I've got a gap in the middle just to draw out the transition state. These types of reactions have been studied extensively by many research groups, including the Paterson Group itself. With a combination of experimental results and computational studies, it's actually thought that a reaction like this proceeds via a 6-membered ring transition state, but the lowest energy version of that is not actually a chair, it's a boat. Just using some color to differentiate the different components here, in black I've got the enolates, in green the boron Lewis acid that's helping to mediate this, and in purple I'll put the aldehyde. So key elements for control are, well, I need the E-enolate, so let's put that in. In the pseudoaxial position, I have the hydrogen, I don't have a choice there. Pseudoequatorial position, I don't have a choice either. The methyl group has to be on the opposite side to the oxygen. Now in the final position on the enolate, this position will always be sp2 in the transition states, all the way through the thing. On that center, we need to reflect that restricted rotation in the enolate itself. So maybe something like this will be good, where the hydrogen and the methyl group in the 1,3 positions are eclipsing. Now, the transition states for these are understood to be controlled by one further non-covalent interaction, and that's an interaction with this hydrogen on the aldehyde. On the aldehyde, well, we prefer to put the R group in the pseudoequatorial position for all the normal reasons, just to get it sterically out of the way. But the hydrogen is now actually quite delta positive. We can see that because it's activated. This isn't a normal carbon anymore. It's thought that this forms a non-classical hydrogen bond to the lone pair that happens to be on the PMB ether. This additional coordination lowers the energy of this transition state and also twists it into a boat shape. Essentially, what we mean by a non-classical hydrogen bond is that the hydrogen isn't attached to a nitrogen, an oxygen, or a fluorine. It's instead attached to a carbon, but that carbon is very delta positive. So essentially, we're saying that the carbon has a higher effective nuclear charge, or Z effective, than normal. And that's only true in this transition state where the boron is activating the aldehyde itself. So this transition state is very favorable because we get this additional interaction. But the other thing that we don't have is that we don't jam this methyl group at the back into the middle of any bulky groups. This helps to differentiate the energy of the two transition states that come from either attacking the top or the bottom face of the enolate. The bigger energy difference between those transition states, the higher DR of the product that we want. Right then, so moving on, we have an aldol product now. The next sensible step is to set the final stereocenter where that ketone is currently. We don't want to carry this aldol product through too many steps, because that hydroxyl group in the beta position to the carbonyl is at risk of elimination or retroaldol fragmentation in subsequent steps. But while we've got it there, we can use it to do a substrate-directed 1,3 reduction to set a hydroxyl-bearing stereocenter at the carbon with a star. Now we need it to be anti, as in we need to send the hydride in from behind. There's two common ways of doing this, and each have their merits depending on what you want to do later in the synthesis. I've already made a more full video on these topics, and it's linked in the description below. One option is to use an Evans-Tishchenko type reduction. That would be using a reagent like this. Essentially a borohydride reducing agent with electron withdrawing groups, which are also leaving groups. And you tend to do a reaction like this in acetonitrile, although other solvents work. But importantly, you need some acetic acid in there. These tend to occur at low temperature. That's just maximizing kinetic control. So minus 20 degrees C is pretty common. The product that we get is this diol, which has been set 1,3 anti. And just quickly how that works as a transition state, it's going to look something like this. The borohydride reagent condenses onto the hydroxyl group and eliminates an acetic acid molecule. Acetic acid itself will activate the carbonyl. That's the one that's going to get reduced. And now we can use another Zinnemann-Traxler type transition state. The lowest energy transition state will be this one with a chair. There's likely to not be very many other competing interactions going on. And all we do is fire in the hydride into the carbonyl group. That gives us the anti-relationship between these two stereocenters that I've just highlighted with red arrows. Why this transition state is the lowest in energy is, of course, all of the R groups that are around the edges have all been able to be put in pseudo-equatorial positions, which is great for a chair. Just popping up to the top of the slide, there is an alternative method that goes through a slightly different product, which is the Evans-Tishchenko reduction. This uses samarium diodide, but interestingly for this discussion in a catalytic amount in the presence of propionaldehyde to do the same sort of reduction, but there's a key difference. We get the same hydroxyl stereocenter by delivery of a hydride to the ketone, but at the same time, we get left behind an ester on the hydroxyl group that was being used to direct this. So in principle, we're setting the same stereocenters, but to all intents and purposes, what we've done here is protected one of them, and that would allow us to easily differentiate between the two, should that be important in a future synthesis. When this combination of reagents is added to an alcohol like we're doing here, essentially what happens is we form a hemiacetal. I'm just going to ignore the oxidation state and the spectator ligands on the samarium just for the time being, for the sake of clarity. But essentially what we're doing here is developing a hydride type nucleophile that can use arrows such as this. And there's scope on the samarium to coordinate a carbonyl group. And so we can get an intramolecular type delivery again. So much like before, we can set up this highly chelated transition state that should also be able to direct addition of a hydride in the same 1,3 antisense as the Evans-Tishchenko reduction. So how do we make a choice? Well, both of these transition states look pretty decent. We should expect high DR here. In both cases, we're able to put everything we want to into pseudo-equatorial positions. So there's nothing fighting against forming this transition state. Under kinetic control, this should be the major pathway. And indeed, that's what's observed experimentally. Both of these reactions go in very, very high DR. So it comes down to a question of, do you want the two alcohols free, in which case the Evans-Tishchenko reduction is fine? Or do you want to differentiate the hydroxyl groups, in which case you should do the Evans-Tishchenko reduction, which will do it for you at the same time? Another key consideration here, though, is what sort of scale do you want to do this reaction on? And I'm going to use that as the key distinction here. The Evans-Tishchenko reduction forms a bit of a slurry, which you're holding at a low temperature, and you need to use a stoichiometric amount of your reducing agent. In fact, you probably need to add a lot more than that. So the Evans-Tishchenko reduction might become slightly less practical at larger scales. Now, the Evans-Tishchenko solves that problem for us. We can lower the samarium iodide loading down quite a lot. It's not unreasonable to do this reaction in single-digit mole percent loadings. I think that's the superior choice here. The intermediate we're making is really early in a very long total synthesis. We need to get access to rather a lot of it. And so I'm going to progress forwards using the Evans-Tishchenko reduction. One final thing that you might think when you're planning your synthesis is we've got to be careful about what our future steps are. The next step that we're going to do is to isomerize the alkyne into the diene. And that's going to involve using some acid, it turns out. So there's a reasonable argument that the Evans-Tishchenko is also superior based on the next step. For example, if I use the diol from the Evans-Tishchenko reduction just here and treated that with acid, there is a reasonably big risk that we protonate that ester, and the alpha beta unsaturated nature of it means it has an electrophilic center 6 atoms away from a hydroxyl group. If we're not careful, we could form a 6-membered ring here, which is not what we really want to do at all. Now, it turns out that this cyclization is outcompeted by the Alkyne isomerization that I'm about to draw out, but it would be very tough to know that on paper in advance. We can see that that's not a problem for the Evans-Tishchenko product because the nucleophile in the reactive position has been protected by this new ester group. There's no longer a nucleophilic lone pair in a 1,6 relationship to an electrophile. So pushing forwards, let's use the Evans-Tishchenko reduction product and move on to the Alkyne isomerization. Now, it turns out there's a really simple procedure for this. All we need to do is add triphenylphosphine in the presence of phenol. So that's the source of acid I was talking about before. Now, this isomerization from the alkyne to the diene was originally demonstrated by Trost, some links in the description below, but was adopted in a variety of other total syntheses since the early 1990s. I think distinctly non-obvious what the mechanism for this is, so I'll just doodle out the proposal. We start with our alkyne, which is of course electrophilic in the beta position, and that will be attacked by the soft nucleophile. That will reversibly form this intermediate here, which is the key one for the next step. Now, the formation of this might have been helped by the acid present as a catalyst, but importantly, we do need this overall neutral molecule for the next step, as it needs to be able to pick up a proton somewhere else. And guess what I'm saying is we can't have an intermediate with an overall positive charge, say if there was a proton here, as it won't be able to react as a nucleophile itself. But that's okay, these will all be in the mix. We can pick up a proton from the phenol on the alpha carbon. I guess that's quite likely to happen on the opposite face to the phosphorus, but it doesn't really matter because it's all in equilibrium anyway. Next, I can enolize again, just in a different position. And similarly, this intermediate can pick up another proton in the alpha position, just standard enolate chemistry again. We now have a slightly different type of proton on the delta position, just highlighted here, that can be removed. And that's reasonably acidic because it allows us to go to the Iodide structure. And now we're getting quite close. Essentially, what we're doing in this step is just finding a way to transfer a proton. So that Iodide could also pick up on its proximal position just here to generate us this intermediate. And now we're just an elimination away from the product that we want, perhaps something like this. Now, overall, this is under thermodynamic control. We can see that from the reversibility of the steps, but also from the fact that we've picked an acid, for example, that's going to behave rather reversibly with the types of pKa's involved in these steps. This works remarkably well. I think isn't particularly well known and is a really excellent way of making diene when you're next to an electron withdrawing group like the ester that we have here. And now finally, we're at the end game for the synthesis of this intermediate. Essentially, we have the coarse skeleton, but we just need to do some protecting group jiggery-pokery, which was important for the later total synthesis of the bigger molecule that this is only a part of. Firstly, this ester has done its job now, so we might as well just take it off. Some pretty standard mild conditions for this would be to use potassium carbonate and methanol. You'll hear British people calling that pot carb and American people calling it K-carb. Who knows why there's a difference there? This is just a slow release generation of methoxide ions, and then they can go in and do their job in cleaving that ester. Some reasons why we need it to be quite mild would include, we don't want to deprotonate here. I mean, there's all sorts of things that could happen there. Maybe we could form a six-membered ring by attacking onto the delta position of this alpha, beta, gamma, delta unsaturated ester. Let's try and avoid that. A more trivial thing would be that the propionate ester migrates to the other hydroxyl group, but then we'd hope it would fall off later anyway. Another thing we wouldn't want to do is deprotonate this proton here, because that might lead to E1CB elimination, and we'll lose the stereocenter that we spent all the time making. Using the methoxide anion is sensible, of course, because even if it attacks at the other ester, we won't notice any difference, unless we did some radioactive labeling or something, as we've just got the methyl ester in there anyway. Okay, now we've got this diol with these acidic protons in here. We were going to protect this, and we were going to protect it as a PMP acetal. That's quite easy to do. Although we could use anisaldehyde to do this, this dimethyl acetal is probably the superior reagent, and it keeps itself dry because any water that gets present in this step will just cause the reverse reaction to happen, which will be a total pain. We can use PPTS again as a nice source of mild acid to get this transformation going. The first step, of course, being generating the oxycarbenium ion for forming the acetal, and then we'll have a standard acetal formation mechanism to clip this on. Now, this acetal was formed under reversible conditions, so thermodynamic control is at play, and that's going to account for the high DR at this stereocenter that's just forming here. If we have a think about how that molecule sits in 3D, it's probably going to look something like this in its lowest energy conformation. So we've got 4 substituents that could go pseudo-equatorial on here, and it looks like we're picking the ones that are locally biggest to minimize 1,3 diaxial clashings. So that's this group on the left and the aromatic group. Both of those have local branching, which will just increase their size a bit. Think of them like isopropyl groups, I guess. Whereas if we look at the other 2 substituents, they're a bit smaller. There's a methyl group and something that's closely related to an ethyl group. So we could argue this with the normal A value rules, when considering chair conformations of a six-membered ring. Now, of course, this might not actually be a perfect chair, but in the very least, we could model it like this, which would allow us to check in the lab whether we've actually done some of the steps correctly. For example, we could now use the 3J vicinal coupling values in the proton NMR spectra to tell us something about the shape of this ring. So that would be looking specifically at these protons here, and the coupling constants that we see would tell us a lot about the conformation of the ring. Another thing we could do here to infer the stereochemistry of the acetal proton, that's this one at the back, we'd probably expect it to have an NOE, that's a nuclear Overhauser effect. That's another NMR technique that I don't want to go into the details now, but it tells us whether protons are close together in space, regardless of the bonds in between. We'd also expect there to be NOEs, say with this methylene group as well. So this choice of protecting group has also given us some extra information that might be useful in the synthesis at some point. Okay, back to the forward synthesis. Next thing we're going to do is take off this PMB protecting group. Now the reagent used here is a thing called DDQ. This is an organic oxidizing agent with this structure, and it's used in various reactions, but one of the main ones is to deprotect these PMB groups specifically, and the oxidation mechanism involves radicals, and at some point we need a water nucleophile. So in principle, we could just add water here, but one of the problems with this is that this mixture will get a little bit acidic, will actually form phenols as the reaction progresses, and we oxidize that quinone ring into a diphenol ring. So in the actual synthesis, forming an acid in here will be a right pain because we've just put that acetal on, and acid and water will just make it fall off again. So to solve this, what we do is we just buffer it. We want to keep it mildly basic in this procedure. So we can just use a combination of dichloromethane that helps keep things soluble, and the pH 9 aqueous buffer. These things are just commercially available and most labs will have them kicking around somewhere, and that will stop any side reactions happening for us. Going forwards, there's two more things we need to do. We need to turn this alcohol into an alkyl iodide, and we need to turn this ester into a silyl ether. So there's an order to choose here on which one we go for first, and we'll see why in a second, but it's going to turn out to be best to make the alkyl iodide at this point, even though notionally it's more reactive and we probably don't want to carry it around for too long. So to make the alkyl iodide, I need triphenylphosphine in the presence of diatomic iodine. We also need to make sure there's a mild base in there, and imidazole is quite a common one to use. This will mop up the hydrogen iodide byproduct, which of course is really acidic and would mess around with our molecule. Imidazole is just this heterocycle, which can act as a mild base. And that will give me this product here. The mechanism for this reaction is a modified Mitsunobu or apple type reaction. The mechanism starts by nucleophilic attack of the phosphorus lone pairs onto the iodine. That gives us an electrophilic phosphorus center, which would love to form a much stronger bond to the oxygen than to the iodine, and luckily the iodide obliges and acts as a leaving group. In this step, we can lose a proton as well. This is where we lose Hi, and the imidazole comes to the rescue and hoovers that up for us. That makes the oxygen into a leaving group, and that can easily do an SN2 reaction to form triphenylphosphine oxide, which is the driving force, and the alkyl iodide. So I think the triphenylphosphine oxide is doing the heavy lifting there with the thermodynamics, because a carbon-oxygen bond is of course stronger than a carbon-iodine bond in terms of bond enthalpy. And now we can kind of see why it was a good idea to make the alkyl iodide at this point. The main thing we might want to worry about is whether those double bonds are compatible with diatomic iodine, because of course CC double bonds do react directly with iodine, and we might trigger another reaction that we don't want if we're not careful. But luckily here, we've got this ester attached to the diene at the moment, and that makes the CC bonds non-nucleophilic while we're doing this transformation. They're not likely to react with the I2 and make some other byproduct that we don't want. And now we're ready to finish this off. We need to reduce that ester and turn it into the silyl ether. Now, on first glance, this looks like we should use some sort of hydride reducing agent. I mean, we could go in all guns blazing with, say, lithium aluminium hydride or maybe lithium borohydride to reduce the ester down to the alcohol. But there is a chemoselectivity problem here. These reagents are generally considered to be on the hard-soft borderline as nucleophiles. So actually, there are other positions where these could react. So whereas we want direct addition to the ester, we could easily get reaction at the beta position here, or at the delta position here. Or even worse, these reagents can react with alkyl halides, particularly iodides. So there's every possibility we'll lose our iodide and it'll be reduced out completely to a methyl group, destroying all our hard work. So that's no good. We need a better plan. And to solve this chemoselectivity problem, we just use dibal in excess to reduce down to the alcohol. Dibal has a dimeric structure like this, which can release this Lewis acid out of there. Note that that's not got a minus charge on it at the moment, so it's not a reducing agent as is, but if it can find an oxygen lone pair, it can become a reducing agent and activate the carbonyl center right next to it to get direct addition. Now, if you use these reagents a bit more carefully, sometimes you can get this to stop at the aldehyde, but in practice, most of the time, this will go down all the way to the alcohol, particularly if you have the dibal in excess and you're not at a particularly low temperature. So this works to take us all the way down to the alcohol. And then to finish off this intermediate, all we needed to do was put a silyl group on. Multiple ways of doing this, but a way would be to use TBS triflate just being a leaving group in the presence of 2,6-luteadine. So TPS triflate just has the structure like this, where we've got a really good leaving group on the silicon. This is just a much more reactive version of the silyl chloride reagent. And when we're so many steps into a synthesis, that might just become preferable to make sure that the reaction happens quickly and cleanly. For example, we don't want that acetal messing about if you've got slightly Lewis acidic conditions. The standard compatible reagent with TBS triflate is not actually to use triethylamine or pyridine. You tend to use luteadine, which is just a more hindered pyridine like this, with methyl groups flanking the nitrogen. That's just a hindered base, and it stops it playing around elsewhere in the reaction. And after all of that, we've got our completed intermediate ready for future steps, which in fact would involve an SN2 reaction at the alkyl iodide to couple this fragment into a bigger total synthesis. I covered quite a lot of chemistry in this video. If you want some more detail on some of the mechanisms involved, please do have a browse of my channel, as hopefully you can find some answers there.